below the plates. We're going to cover that in a second and why that can happen as well too. Okay. So charging. Rule of thumb, deep cycle lead acid batteries, wet flooded. Jeremy, what was your recharge rate that you guys push for your product?
100% of the amp hours in amps.
And the rate that it goes back into the battery for your group 31, for example?
Oh, 7.5 amps per 100 amp hours.
So at Jeremy's product with an AGM product, pure lead acid or pure lead AGM product, 7.5 amp rate. You can see that with wet flooded product on the deep cycle side, you have a significant uptick in the amount of input current required for the battery at that point. In the world of charging today, guys, there's been some big changes in the past 10, 12, 15 years of actually charging the battery back up and the type of technology being utilized in today's chargers versus what was being utilized 10, 15 years ago. I play a lot in the golf world. Golf cart batteries, electric vehicles are powered by my product for the most part. And the typical comment that I get from a golf course pro these days versus what I was hearing 5 or 10 years ago is that you guys must be taking lead out of your product because lead's getting so expensive. You're trying to keep costs down because we're not seeing the batteries last as long as they used to 5, 8, 10, 12 years ago. And I can tell you that the 3 primary wet flooded deep cycle suppliers in the country today have not only taken not lead out of the battery, they've actually added more content to the product over the previous 5 or 8 or 10 years. What we've seen in that time frame is a complete migration in charger technology. Charger technology back in the old days was ferroresonant copper transformer type charging, where if a battery charger was rated at 36 volt 25 amp, you actually could put out about 22, 23 amps into a fully discharged battery bank and bring that battery bank up rather rapidly. The migration to high frequency charging in today's world, chips and diodes, leads to a much higher buildup of heat content within the charger box itself, which really cuts back on the charging's performance at that point. And where you have a rating of 25 amp in a 36 volt system coming out of a 110 AC outlet in a fully discharged condition, you might see half of that number actually coming out of the charger box when it's all said and done. So think about that from a standpoint in migration and charger technology to all the various applications that utilize deep cycle batteries. And I'm going to default again to the golf cart world, so just bear with me for a second. If you got a guy with a fleet of golf carts on a golf course with 50 carts, and they're trying to get 18 to 36, let's say they're trying to get 36 holes per day out of that cart, and it's on the tee box at 7 o'clock in the morning, finishing up at 8, 9 o'clock at night in my neck of the woods because the sun stays up late, that battery is going to be completely depleted by the time it goes into the cart barn at night, right? Well, if I've got 36 volt, 25 amp rated charger that's actually putting out 12, 13, 14 amps because of the change in technology of charging over the previous 8 to 10 years, there's a damn good chance my battery bank's not going to be fully charged by 7 o'clock in the morning when the first tee goes out, right? Not only is it not charged, but the battery still is retaining a whole bunch of heat during the charge cycle. And the combination of putting that discharged battery out in a high heat environment that it's in when it goes out is not good for battery longevity. So when we look at a charge cycle and the amount of current that has to go back into the battery, we want to see at least 12 to 15 amps of input current per 100 amp hour of battery bank capacity in a wet flooded deep cycle product. And we have found that with this ratio of that type of amperage going back into that capacity of a battery bank, we can get that battery bank topped off in about 7 to 8 hours max, which then allows for about 3 or 4 hours of cooling off or rest period before the next discharge cycle occurs. And I think what you guys are going to have to do to some extent, where you guys are sourcing these chargers, it becomes just as important of where the batteries are coming from, believe it or not. So there's a lot of different options out there. There's some research that you guys have to do, determine what technology is being utilized in which charger box to best marry with the battery bank to get the longest possible life. Because if you look at the battery as the gas tank, and you look at the battery charger as the gas pump, they both got to work, right? And if they're both not working, you're going to have problems with longevity, performance, and eventually premature failure.
How long did you say that it would take to charge that up?
So the ratio that we're using here of 12 to 15 amps per 100, it's based on the fact that we're not discharging the battery beyond 80% depth of discharge. So in a true deep cycle battery, wet flooded, we can take that battery down within the parameters that we play within, to about 80% down, meaning there's 20% left in the battery at that point. If we utilize that as our yardstick, 12 to 15 amps of input current per 100 amp hour of battery bank capacity leads to a recharge time of no more than 6, 7, maybe 8 hours, which if you're looking at shifts, for example, gives you then enough time to recharge the battery bank fully, allow that battery then to rest or cool before the next discharge cycle occurs.
How many volts per cell do you figure is 80% then?
That's easy. We can, just math my head real quick, hold on. So 50% stated charge is about 1.9 to 2.0 volts per cell. So in a 12 volt battery, for example, or let's use a 6 volt battery for golf cart purposes as an example, you're looking at 6.00 volts at 50% state of charge, open circuit voltage with no load.
Okay.
Okay.
So,
So the solution then, I mean, or, you know, a possible solution is that you just need to either have the battery charger from a capacity standpoint to be able to recharge the battery bank. You have to limit, or you could limit your depth of discharge, or some combination of both of those things to keep that battery in the queue you want to keep it in, to go for what I call that perfect cycle. And the perfect cycle is not beyond 80% DOD, fully charged, 1.265 gravity to confirm it, and then 3 to 4 hours to rest before the next discharge cycle occurs.
So how do we do that in our industry?
Yeah.
Of all the different batteries, different types, different makes,
Yep.
and then you wheel out your Craftsman charger and dump it on a battery.
Yeah, what it goes back to is obviously we don't have time to go through all this when it's said and done. So if we're talking about a serviceable product that we have access to the cells with, the hydrometer, refractometer is your best friend, always and forever. Okay.
Can we talk a little bit about charging for rigs that have a continuous draw on them?
Yeah.
And what kind of charger to get into
Yep.
to not be cooking them if they sit over the weekend, but still charge them enough if it's just sitting on 8 hours overnight?
Yeah, so one of the worlds I play in with deep cycle storage batteries is the off-grid renewable energy world, right? Where you have a constant flow coming out of the battery because everything on that side of the inverter in a renewable energy system goes through the battery and then out to the inverter to invert to AC. So the bottom line is that what I foresee with that type of a product is that you measure what your draws are that you have to power, parasitic or otherwise, and then you make sure your charging current coming in from the backside is equal to or even slightly greater than that to offset what's coming out of the battery on the backside. It's going to vary on a case-by-case basis. It all depends on what your draws are at that point. I can tell you that there is a thing with flooded lead acid batteries called short cycling, which can be an issue in those types of applications that you're talking about. And you're probably looking at that point of something more of a pure lead AGM design to best withstand that short cycling characteristic the battery's exposed to.
Yeah.
It's an issue.
See, it used to be an issue for me because in the day, you didn't have a parasitic drop.
Right.
Nowadays, with NDCs and automatic vehicle rotation and all that, everything has to stay on the night, so I'm at 5 to 7 amp draws.
Always.
24/7. So when I'm coming to my onboard charging units, I'm doing what you said, I'm going a little bit above and just hoping that when that guy goes on a week vacation and it's sitting there, it does what it's supposed to do and not cook the battery.
Yeah, and on top of that, if you go back to my old-fashioned technology of wet flooded, then you've got a problem for gassing. And if the guy's gone for a week and you have enough gassing occur within the battery where your electrolyte level is dropping without being returned in the form of distilled water, you're gonna have a burnt up battery by the time you get back back on service again. So in those particular applications, it becomes, again, price, quality, and serviceability of the product, right? I'd have to say in your world, it sounds like something like a pure lead AGM design is probably the way to go because it can handle that much better than a wet flooded product could. No question about it.
Hey Chip, can you cover the thick plate AGM a little bit, difference in
Yeah.
the charging algorithm?
So there, as Jeremy mentioned more than a few times, there's various types of lead acid technology out there. My company, because we focus 95% deep cycle storage product, we've also built some AGM batteries as well. Our AGM product differs in the sense that it's really designed to be discharged 80–85% continuously for hundreds and hundreds of cycles before the battery actually fails. Realize AGM technology is not new, it's been around forever, right? Primarily though, AGM product until the last 5, 6, 7, 8 years has been for standby power. Emergency exit light signs that have those little brick batteries where it's basically on a constant float voltage 99% of the time. The grid goes down, the battery lights the sign until the battery's dead or the grid comes back up again, right? So customers, because of the maintenance-free aspect, or I should say end users, because of the maintenance-free aspect of AGM, initially tried using those batteries in cyclic applications, daily, weekly, monthly, where they were cycling the battery. It didn't work because the battery wasn't designed to do that. So because what we do is more of a cyclic cyclic application down to 80–90% depth of discharge. When we developed an AGM line, we built it with a thicker grid, thicker plate structure to best withstand the acid transfer process of lead acid technology to get lots of cycles out of the product when it's all said and done. So if you've got something that's sitting for a week or 2 or 3 weeks at a time, that's bringing the battery down to a relatively low voltage, maybe deep cycle becomes a better look at for you than something that's a standard starter AGM battery at that point. So you have to, it really, man, you gotta put on your detective hat these days, guys, is what it boils down to. And try to find somebody who's willing to give you a non-bullshit answer about what the product can and can't do, which I know can be difficult in today's world. So. Okay. Questions or comments?
Well, a question like, it's not really related to the fire industry so much, but say solar chargers, when we start talking about solar chargers with solar panels,
Yep.
that's still not about the kind of amperage that you're talking about for charging these batteries.
And I've seen these try to work in the golf cart world, for example, where they put a panel up on top of the roof of the golf cart and say, hey man, this panel will keep this battery bank charged. Well, relatively speaking, today's solar panels put out, or I should say are rated at between 250 and 300 watts, okay? Understand that that rating that's applied to that technology is at peak. So when is a solar panel at peak?
No clouds.
No clouds, and you got a 90-degree angle of PV on the panel at that point, right? At that point, you're at peak. You're at 250 to 300 watts. In the real world, unless you've got trackers and some other things, you've only got about 80% of that rated capacity to be able to really produce from that product, okay? So if I've got a 300-watt rated panel at 80%, I really have 240 watts of deliverable current over a period of time, okay? Well, going to Ohm's theory,
Ohm's law, theory.
inside joke between Jeremy that Steve let me in on the hook with last week. Ohm's law is what? Watts equals volts times amps, right? So if I've got 240 watts of current going into a 36-volt battery bank, an electric vehicle golf cart, take my 240 and divide it by 36 and I come up with about 7 or 8 amps. Sound about right? I got 7 to 8 amps of input current coming off of that one panel to charge a 230, 240 amp hour battery bank.
You don't even have enough to push it.
And especially if the batteries even get slightly discharged at that point, resistance is building up within the battery bank, and that current's not going to punch through, and you're going to have it's just not going to keep up. It feeds into the watering system, and then as the water runs through the tubing system down into the cell, as the fluid level in the cell rises, it pushes the float up into the underside of the valve and chops the fluid fill rate at that point at the right time, all the time, every time. So for a 6-pack of golf cart batteries there, you're literally looking at probably 10 to 15 seconds of watering time versus popping every single cap, trying to keep it from turning into a big old mess, and then trying to put it back on again.
So that just stays on the battery then, the single point filling system?
Never come off, yep, for sure. So, a couple things that you guys can take a look at here for when you have a battery or a suspected battery problem. there's basically 3 or 4 things that we want to walk through here real quick. We're just going to blaze through these because you guys are probably doing these for the most part already. Visual inspection tells you a lot, right? Who knows how to read date codes on the side of the battery? Okay. For those who don't, the default system, did you guys do this?
What's that?
You guys do the letter number thing or no?
Yeah, but we skip I and E.
The AGM guys make it so damn difficult.
No, not AGM guy, just us.
Got it. Oh, okay.
I can go.
So typically in the industry, it's a 3-character code. Typically on the side of the battery somewhere, it's a sticker, maybe 1 inch by 1 inch. And that 3-character code is the first character is a letter. A, January, B, February, C, March. And then the second 2 characters are the year. So batteries that we're shipping this month, for example, would have a D17 date code for April of 2017. Really helps you with your rotation and shelf life issue as well. So if you see something with a D16 date code on it, check it real quick before you stick it into the application and charge it if necessary. If you're checking a battery that's problematic and you see a date code of D14, D13, and it's a deep cycle battery, you got its life, replace it. No more inspection necessary with the product when it's all said and done. Open circuit voltage, when you're checking open circuit voltage, always make sure surface charge is depleted first, so hit it with a quick load test. If it's just coming off of charge. Cell inspection, check the electrolyte level, the appearance, and then do a hydrometer check. The appearance of electrolyte is important as well. Clear electrolyte versus cloudy or dark electrolyte, what do you think indicates? The active material is breaking down off of the plate and it's beginning to float within the electrolyte solution. If you see a massive amount of sediment or material within the electrolyte, there's a pretty good chance the battery's pretty much shot at that point. Okay. And then a closed circuit load test. So we do these just from a training standpoint for our distributor dealers. My favorite one is, that a warranty? The terminal's missing. Loose connection for a meltdown is basically what we're talking about. Terminal damage, obviously a battery that's been boiled dry, plate growth in the lower right hand, and you've got a battery overcharge situation over there where the active materials is basically falling off the plate there at that point. Visual inspection would be battery age, terminal condition, container condition, cable connections, presence of corrosion. This type of product right here, believe it or not, guys, if you put if you use an open circuit voltmeter and stick the negative on the negative terminal and put the positive lead into the dirt on the cover of the battery self-discharges to the dirt that's on top of the battery. You have voltage loss coming through the current between the 2 terminals, passing through the sediment on top of the battery. It's always important to keep the batteries in a nice clean condition. Okay. As much as a volt sometimes, believe it or not. And then cell inspection, the hydrometer doesn't lie, 1.265, 100% state of charge. Fully discharged is 1.140. A variance of 50 points between cells indicates, in our world, a bad cell. And the 50 points is measured on these last 2 numbers on your gravity readings here. So if I've got a 6-volt golf cart battery and cell 1 is 1265, cell 2 is 1265, and cell 3 is 1215, or even greater discrepancy, probably time to replace the battery at that point. We've already covered open circuit voltage. There's a cheap load tester there. We'd much rather see something with the carbon pile taking a little bit of a better bite out of the battery during the discharge test. Questions or comments? So, in the world that I play in with wet flooded product, as much as we pride ourselves on what we think is a high-end, high-quality product, we also put an awful lot of responsibility and accountability on the actual user of the product. And the 2 things you guys really need to be watching out for with wet flooded deep cycle product is make sure the batteries are getting back to a full state of charge after each discharge cycle, and making sure that you're checking the proper electrolyte levels after the batteries have gone to a full state of charge so that the batteries aren't getting burned up. You do those two things with any wet flooded product, you'll get great life out of it when it's all said and done.
On your last
Or
slide,
just buy a gas or golf cart.
Yeah, loud, dirty, not green, the whole 9 yards. Go ahead.
on your last slide, did it say 0 was 11.6, because I thought it was 10.5.
It is 10.5. If it's 11.6, it's a typo. I don't know why that's in it. Yeah, this is 10.5. 1.75 volts per cell is 100% depth of discharge. I don't know why it's in there like that.
11.6, that's 50%, right?
Probably somewhere between 35 and 40% state of charge, right around there somewhere. Okay. Any other questions or comments? Now go ahead, guys.
That's a lot of information.